divisibility test by 7. So if any number is divisible by 7 or not, we will check its divisibility by 7. For example, 84. So what is the process? So our step 1 is multiply the last digit by 2, and step 2, subtract from the remaining digits. If this difference is 0 or divisible by 7, then our number will be divisible by 7. So let's see. So the last digit is 4. We will multiply 4 by 2, we get 8, and if we subtract 8 from the remaining digit, 8 minus 8 is 0, so 84 is divisible by 7. Similarly, if we take suppose 147, so here the last digit is 7, we will multiply it by 2, we get 14, and if we subtract 14 by the remaining digits, we get 0, hence 147 is also divisible by 7. If we take one more example, suppose 156, so here last digit is 6, we will multiply 6 by 2, we get 12. Now if we subtract the remaining digit by 12, we get 3, and 3 is not divisible by 7, hence the entire number is not divisible by 7. That's it. Thank you. Divisibility test by 13. So in this video we will be seeing the divisibility test by 13. So most of the students are often confused in this, so let's see how we will do this. So suppose a number is there 143, so how to know that this number is divisible by 13 or not? So the steps we will be following is step 1, multiply last digit of the number by 4. Step 2, add this to the remaining digits of the number. Now the sum that we get, if it is either 0 or divisible by 13, then our entire number will be divisible by 13. So let's work out with our example. So here the last digit is 3, we will multiply 3 by 4, we will get 12. If we add 12 to 14, we will get 26, and we know that 26 is divisible by 13, so our number 143 is also divisible by 14. Let's take another example. Suppose 273, here the last digit is 3. Let's multiply it by 4. We get 3 into 4, 12. If we add 27, the remaining digits with the number we got 12, we get 39. And we know that in 13's table 39 comes in the third multiplication. So our parent number 273 is also divisible by 13. So thank you. So let's see how to find the number of trailing zeros at the end of n factorial. So questions are like, what is the number of trailing zeros in 100 factorial, 30 factorial, 50 factorial? In those questions you can't just multiply and see the number of trailing zeros. So here what we basically do is we count the number of 5s. Why? Because the multiplication of 5 with any of the even number will give you 0, and we know that like in 100 factorial we will get at least 50 even numbers. So there is no shortage of even number. So you just need to find the multiples of 5 and you will get the number of trailing zeros. So to find the multiples of 5, what we will do is, suppose n factorial, we have a formula n by 5 floor function n by 5 square plus n by 5 cube and so on. So floor function, if there is an integer inside it, we will get the integer as it is, and if there is an integer which lies between two integers, we will get the value which is the lower of the integer. 7, 8.7, again we will get 8, like floor integer of the greatest integer function or floor integer function. So let's take an example. So for example, suppose 100 factorial. So we have to find the number of zeros in this. So the formula will be 100 by 5 plus 100 5 square plus 100 5 cube plus 100 5 4 and so on. So after this, you know that this is lying between 0 and 1, so the floor value will be 0. Here also it is 100 by 125, so it is also 0 between 0 and 1, so here also floor value will be 0. Here it is giving 20, so our greatest integer value of this will be 20. Here it is 25 divided by 100, which is 4. So what we are getting 20 plus 4 plus 0 0, okay, so 24. So we can say that the total number of trailing zeros in 100 factorial is 24. So I think you have understand the concept. Thank you. So today we will see this new concept, cyclicity of numbers. So these types of questions you have often seen in the exam, like 2 to the power 54, what is the unit digit? Similarly, unit digit of 2 to the power 323, similarly unit digit of this multiplication, and similarly unit digit of these types of problems. So you can't manually find, you can multiply. These numbers are so big that you can't try even to multiply so big number. So we will see how we will do this. Suppose unit digit of 2 to the power 363. So in this case, what we will see is that if we take suppose 2 to the power 1 is 2 at unit digit, 2 to the power 2 is 4 at unit digit, 2 to the power 3 is 8, 2 to the power 4 is 16, so 6 is at unit digit, 2 to the power 5, then we get 32, so 1 2 is at unit digit. So you will see that after 4 it has started repeating. 2 to the power 6 is 64, see again it has started repeating. 2 to the power 7 is 128, see again it has started repeating. So 2, 4, 8 and 6, these are the cyclicity table of 2, that if we suppose 2 to the power 1 is last digit is 2, 2 to the power 5 the last digit will be again be 2, 2 to the power 9 again the last digit will be 2. So after every fourth interval we will find the 2 as repeating unit place. Similarly, if 2 to the power 2 is 4, 2 to the power 6 will be also 4, and 2 to the power, suppose 14 will be also 4. So by this is the cyclicity table for most of the numbers, like from 1 to 10. So we don't need to learn them, because in a question anyhow we will have sufficient time to see the last digit. So this is the question that I will be trying to solve, and it will clear most of your concepts. So let's see how to deal with such questions. So here 11 to the power 11, 12 to the power 12, so it is a sum and we have to find the last digits. So for unit digits, you don't have to worry about the tens place digit. Okay, so just eliminate that. So we can write it like this: 4 to the power 14 and 5 to the power 15. Now we will find for every digit we will see what is the cyclicity. So for 1 we know that at a unit place we will get 1 only. For 2 we know that when it is 2 to the power 1 is 2, 2 to the power 2 is 4, 3 is 8, 2 to the power 4 is 6, and again 2 to the power 5 we get 1. So here at 12, so 12 will be multiple of 4, so we will get 6 at unit place. Now if we see for 3, so for 3 square 9, 3 27, so 7 is the last digit, 3 4 81, so 1 is the last digit. So if you find, again it will start repeating. 5 is 243, so 3 here last, which is repeated. 4. Okay, so for 13, like for in the 3 to the power 4 we will get 1. So if we divide 13 by 4, so we will get 1 as remainder. So means at 1, again at 1 we will have to come. So 3 will be the unit place digit. Similarly for 4, if we see 4 square is 16, so 6 we will at the final unit place. 4 cube is 64, so again we will 4, so either we will get 4 or 6. So here the cyclicity of 4 is either 4 or 6. So when it is odd number we get 4, and when it is even number we get 6. So here we can see even power, so we will get 6. And for 5, if we see that at any power of 5 we get 5 only at units place. Oh, like here also 25, so we will get 5. So now it has become very easy. So we just have to see the repetitions that occur. So this 1 plus 6 7, 7 plus 3 10, 10 plus 6 16, 16 plus 5 21. So 1 is the answer. 1 is at the unit place. So I think you have understood the concept, and you can practice more questions based on this concept. So I will see if I could add more questions in later videos. Thank you. So let's see remainder theorem. So whenever expression, suppose a into b into c is divided by n, then the remainder of this expression is equal to AR into BR into CR divided by n. So what is AR, BR and CR? So AR is remainder when A is divided by n, and BR is remainder when B is divided by n, and CR is remainder when C is divided by n. So for better understanding, let's see an example. So suppose 15, 17 into 19 is divided by 7. So 15, 17 into 19 is divided by 7, and we have to find the remainder of this. Take, so its remainder will be equal to the remainder if this is divided by 15, and what is the remainder? It will give the same remainder. So you can see into R 17 7 into R 19 7 by 7. So this difficult expression which was looking like a scary one, AR, BR and CR, is what it was nothing but when we divide the denominator 7 to the numerator and what the remainder we get, so both the expression will have the same remainder. So you should fit this thing in the mind. So this will help you to visualize. So here what will be our remainder? 1. here what will be our remainder? 7 and 7 to the 14, so here our remainder is 3, and here our remainder is 5. So if we see, so net 3 into 5 is 15 by 7. So in this case, what is the remainder? 1. So now we will see a better question, like a more difficult question, so that we can have a good practice. So what is the remainder when 9 to the power of 100 by 7 is this? So we can expand 9 to the power of 100 as 9 into 9 into 9, how many times? 100 times, divided by 7. So each time we have, if it will be giving the same remainder as 7 is divided by 9, so it will give, when 7 is divided by 9, it will give 2. Again it will give, 7 is divided by 9, it will give 2. Similarly, how many times? 100 times. Okay, so what will be our to the power of 100? 7. So we can see that 9 to the power of 100 by 7, whatever the remainder is, it is equal to 2 to the power of 100 by 7. If you can understand till this, then the next part is going to be like repetitions. So like 2 to the power of 100. So if of 100 we take out 5 and 20 outside, we are using actually the exponent one, so we are having no problem. So we are not going to write this r repeatedly. So 2 to the power 5 will give us 32 to the power 20 by 7. So again, when we divide 7 to 32, we will get remainder 4. So it will be equal to the remainder given by expression, 4 to the power 20 by 7. Okay, so 4 to the power 20 by 7. Now, so we will take again 4 square and 10. So we will get 16 to the power 10 by 7. Same remainder. So when 7 is divided by 16, we get 2 as remainder. 2 to the power 10 by 7. Again, if we take 5 inside of the power, 2 to the power 5, 2, 7. So again 32 square 7. So if 7 is divided by 32, we get 4 square by 7. So at last we are getting 4 square by 7 as a remainder. So 4 square will be 16, and 16 is divided by 7, we get 2 as remainder. So our net final answer is 2. So that's it. I think this was clear. So if there is any doubt, you can rewatch the video, so it will give you a better understanding. I think I have tried my best. Let's see if I could give further examples in future videos. So thanks. So let's say, suppose a number, composite number, is 75. So we can find the prime factor of this number. So if the prime factorization is written, then it is 5 square into 3 to the power 1. So any composite number can be expressed as a prime factorization. So suppose if let's generalize this concept. If suppose a number n is there, so p1 power lambda 1, p2 power lambda 2, p3 power lambda 3, so on. So the total number of factors will be lambda 1 plus 1 into lambda 2 plus 1 into lambda 3 plus 1, and so on, where lambda 1, lambda 2 and lambda 3 are the powers of the prime factors. Similarly, if the product of the factors is asked, then the number n itself to the power of the total number of factors divided by 2. This is the total number of factors, lambda 1 plus 1, lambda 2 plus 1, lambda 3 plus 1 in multiplication form divided by 2. So let's see, and we will understand this in a better way. So suppose a number 75. So these are the factors of 75. 1 is the factor, 3, then 5, then 15, then 25, then 75. So total 6 factors are there. So how to make up a formula from this? So we can find the prime factorization first. 5 15 bar 15 ja, then 5 3 times. So if you write 75 in prime factor form, then 5 squared into 3 power 1. So there are two prime factor of 75, 5 and 3, and the power is 2 and 1. So the total, if we find the total number of factors, then we know that it is 2 plus 1 into 1 plus 1, which is 3 into 2, 6. You can verify this. We have seen the 6 factors, and this by fit this formula also we get 6. And if we want to find the product of the factors, product of all the factors of 75, then let's see. So 1 into 3 into 5 into 15 into 25 into 75. Now watch very carefully. So if we multiply the first factor with the last one, 1 into 75, you get 75. Now multiply the second factor with the second last one, 3 into 25, you get 75. Now multiply the third factor with the third last, again 5 into 75, 5 into 15, you get 75. So you can see that you get 75 each times. So the value will be 75 to the power of the total number of factors divided by 2. Like you have to, we are pairing, we are getting how many pairs. So here we have got 3 pairs. So power 3 means the total number of factors which you have got by this formula, lambda 1 plus lambda 2 lambda 3 plus 1, total number of factors divided by 2 in power form. N is the number itself. So let's see one more example. Suppose this is a question 360. You can't find the factors of this number individually, or so let's see how we will proceed this by the formula. So number of factors, so we will find the prime factor 180, then 2 times divide 90, then 2 times 45, then 5 times 9, then 3 times 3. So 360 can be written as 2 cube into 5 power 1 3 square. So there are total 3 prime factor, and these are the powers of the prime factor. So now the total number of factors will be, number of factors of 360 will be 3, the first power plus 1 into the second power which is 1 plus 1, the third power which is 2 plus 1. You get 4 into 2 into 3, which is 24. So you don't have to find the number of factors individually. So you can just use this formula, you got 24. So what will be the product of these factors? Product of all factors of 360. So you know that we will again find the pairs. So our formula was the number itself 360 to the power of total number of factors divided by 2, and we know that there are 24, then it will be 24 divided by 2, which will be 12. 360 power 12 will be answer. So I hope you may have cleared your doubt on these types of questions, and you can easily go through these questions. Thank you.